I'm really excited to be here. So today I'm going to talk about some of the recent research that we have been doing in our group. The title of this talk is New Shared Log Abstractions for Modern Applications. So before I begin, I would like to give credits to some of the people who did this work. This is my incredible PhD students, 3 of them. And all of this work was led by another professor in the group, Professor Aishwarya, who also happens to be my wife. And also, I would like to thank the US National Science Foundation, IBM, and NetApp for funding our work. So who am I? So I am an assistant professor at the University of Illinois, Urbana-Champaign Computer Science Department. And this is an incredible place for doing systems research. So if you don't believe me, here's the ranking of top CS departments in the US. This is from a website called csrankings.org. It's totally objective. It's based on the it's totally objective, especially when you show up the top, right? You can see UAUC at the top, just behind CMU, and I had then most of the schools. So this is based on research productivity, right? And previously, I was a consultant researcher at VMware, and also a postdoctoral researcher at VMware. And before that, I got my PhD in CS from the University of Wisconsin. So what do? I co-lead this lab called DASL. It stands for Distributed and Storage Systems Laboratory. And unsurprisingly, we have these 2 main directions in our group, which is memory and storage systems and distributed systems. And the kind of areas that we focus on are fault tolerance, replication, reliability, and more recently, more on resource disaggregation, more storage disaggregation, memory disaggregation, that based on RDMA or more recent CXL technology. And we have also been starting to look at like vector databases, shared logs, and data streaming systems. So we have published a bunch of papers. Here are some of the highlights. Some of these papers have gone on to win Best Paper Awards at all of these top academic conferences. But this is just a sample. So if all of our work is public, it's open, you can just read the papers at this URL. OK, so I'm not going to talk about all the things that I showed in the previous slide. So this talk is going to be specifically about something that most of you are all used to, which is logs, right? Logs have been around for many, many decades now, so we're still talking about logs. Well, the reason is that logs are simply everywhere, right? So if you think about logs, if you think about any kind of systems that you have built in the past, they kind of use the log abstraction, right? You take key value stores databases. They use the log as a write-ahead logging mechanism. They use, if you take file systems, they use the log, which is essentially the journal, to implement file system crash consistency, right? And distributed systems like Consensus use the log for replication. And more recently, modern applications like streaming and event sourcing use the logging abstraction to pass around messages, or the log is actually the data for them, right? And when I say log in this context, I really mean systems like Kafka, right? So when I talk about logs in this particular talk, what I want you to think about is systems like Kafka, RedPanda, or their providers like Confluent or even WarpStream, and things like that, and even hyperscale cloud providers which offer similar services, like, for example, Kinesis or Google PubSub, right? And there are also academic and industry research implementations of these systems which offer you better performance, better properties, and so on, right? So one way to think about all of these systems, which is not a wrong way, is to think about these systems as data streaming systems, PubSub, or message queues, and so on, right? But at their core, all of these systems are essentially a distributed shared log, right? Look, this view is not controversial at all, right? So there was this very popular blog post, which was written by Jay, the CEO of Confluent, 10 years ago, or probably 11 years ago, where he talks about how the log is actually the real-time data's unifying abstraction, right? So essentially what he's saying is that Kafka is a log, and all systems which implement the Kafka API are essentially a log, right? So all of these systems that I showed you in the previous slide, what they export is a log interface, right? And the abstraction that they provide actually is more in particular, the log offers you a fault-tolerant, durable, and ordered sequence of records, right? So when you write something into the log, the records are durable, they are written to multiple disks, right? And there is an implicit ordering of records in the log. And the log exposes a very simple interface to interact with it, right? So at the bare minimum, you can append to the log, where you can take just new data into the system, or you can read contents from the log. So more specifically, if you look at the API, it is very simple, right? So to append, you just give a record, and the log does the record, appends the record, and then returns you a integer, which is just basically the index at which the log appended your record, right? And the read interface is very simple. You basically take the position from where you have to start and read a bunch of records from that point. And the log just returns the list of records. So in the rest of the talk, what I will hopefully convince you is that despite the ubiquity of logs everywhere and their popularity in research and everything, today's logs have a pressing problem, which is they have high latency, and which is not good for many applications. In particular, I'll talk about two kinds of latencies. One is ingestion latency and end-to-end latency. But most of this talk is going to just focus on the ingestion latency problem, right? So that is going to be the first part of the talk. And in the second part of the talk, I'll show you a better solution on how you can design a log, a better abstraction for the log. And this was a research paper that was presented at SOSP 24, which is the Premier Systems Conference, and it won the Best Paper Award there. So the LazyLog idea is like a standard. It's an abstraction, right? And in the third part of the talk, I'll show you how we designed one implementation and how this implementation helps applications improve application performance. So let's get started with the first one. So to motivate this problem, I need to set up some context. So bear with me in this slide, okay? So the shared logs, when I tell you that they give you ordering, what they specifically give you is a linearizable order. What this really means is if you append a record A into the log, and once that is completed, you start another append of B, then there is a guarantee that B will appear after A in the log. So this is the linearizable ordering guarantee. So the linearizable ordering guarantee is very desirable for many applications because it kind of like avoids all sorts of anomalies in the system, right? So many applications depend on that. Many implementations like Kafka and other open source logs provide ordering only within a particular shard, right? So when I say a shard, what I want you to think about is a shard is a fault-tolerant unit which achieves fault tolerance via replication, something like Paxos or Raft or something like that, right? So you have a shard which is fault-tolerant, and you have a bunch of records which are replicated across these three replicas in the shard, right? So here we have 4 records. Now, if you want to scale your Kafka system, what you can do is you can add more shards to the system, right? You can get scalable throughput, but the catch is you don't get total order of records across the shards, right? So there is no way for you to tell whether the first record on shard 1 comes before the first record of shard 2. There is no way for you to tell that. So this has been an academic conquest in the past decade on how to achieve scalable ordering, right? So you want to scale your throughput by writing to multiple shards, but you also want to have total order across the shards. So how do you do that? This problem is solved, and there are many implementations which started in academia and then transitioned to research, starting at Corfu, which was the precursor for Meta's Delos, and there were other systems like SpecLog. Twitter had an implementation, and so on, right? So all of these systems, what they can do is they can scale the throughput by writing to multiple shards, but they can also ensure total ordering of records. So here you can see that there is a total order of records across the shards. You can order them, right? So this is great. You can now scale your throughput and then also get total ordering of records across the shards. Unfortunately, this kind of global ordering comes with a cost, which is high latency, right? So let's take a look at how this happens in a system called SpecLog, which is a kind of a reference implementation for many other implementations. So in SpecLog, there are multiple components that you want to pay attention to, right? So at the left, you have the clients. And at the bottom, you have something called the shards, right? So for simplicity, just assume that it's a two-way replicated shard, which means that it gives you fault tolerance via primary backup replication, right? And there is something called the ordering layer. The ordering layer is just essentially a Paxos cluster, right? So it gives you fault-tolerant ordering. So the way SpecLog works is when you start, the clients first write the records into the shards directly, right? And this gives you durability. So you can see that the shards the primary just replicates the data to the backup. And also, the shards contact the ordering layer to say, oh, how do I record these orders, order these records across the shards, right? And once you get that ordering information from the ordering layer, you return back to the client saying that, okay, now your commands are durable and you have a global order. So this actually incurs 3.5 round trips through the network, right? And it has some batching intervals and so on, batching delays and so on, which actually impacts applications. There's another way of doing this, which kind of reduces the latency a little bit, which is instead of doing the durability first, you do the ordering first, right? So there is an implementation called Carfu. What Carfu does is the clients just first talk to the ordering layer to determine what is the order, right? And once you do that, they take this order and then use that order to replicate the data to the shards, right? So this kind of like alleviates the problem a little bit. It reduces it to 3 round trips. It's still not great, right? But one thing you have to observe here is that by the time the append completes, the records are both durable and they are ordered, right? And this high latency is not just a problem with these multi-shard logs. This also impacts systems like Kafka or RedPanda, right? All of these systems also complete ordering and durability within the shard, right, before your append returns. So as a result of this, both practical implementations and research implementations today incur several milliseconds to ingest data, and this directly impacts applications. So why is this an important problem? The problem is low latency ingestion is very critical for applications. Like, for example, distributed databases, which are actually built on top of Kafka. Example like FireScroll, it actually requires quick durability and low latency. There are several other applications which also have the same requirement. And more broadly, there was this amazing survey by RedPanda Data in 2023. And by the way, this report is public, right? They had this survey where they interviewed 300 practitioners who were using Kafka in production and asked them what kind of latency actually matters to you, right? And about 100 of them, 1/3 of the interviewees said that append latency is the one that they care about, right? So it's a very important problem for them. So you might ask, like, why is this high latency? Why is this problem there, right? So if you think carefully about this, this is actually rooted in the something that we call the eager ordering nature of these shared logs. What do I mean by this? Eager ordering means that when the time you ingest the data, the order is established immediately upon the appends. That is, the commands or the records are eagerly bound to positions within the logs, right? And this is what actually leads to high latency. So in the second part of the talk, what I will show you is how we can solve this problem, right? So the key question that we are asking is, well, the high latency is actually coming from the eager ordering nature of the shared logs, right? Can we avoid this eager ordering, but still give you the same guarantees or the ordering guarantees of shared logs, right, that exist today? So that's the key question that we're trying to answer. So this is probably the most important slide, right? So the key insight here is that although linearizable ordering is required for many applications, it is not required immediately upon appends, but it is required only later when you actually read the data from the log. This is the key insight of the paper, right? So which means that you can be somewhat clever about how you do the ordering, right? And further, the readers are naturally decoupled in time from the writers, right? So you have writers which are dumping data into the system, and then you have readers which are consuming the data from the system, right? And there is a natural decoupling of time between these entities. So based on this insight, the idea is that then you can design a shared log which can actually defer ordering, right, during appends, but establish it just before the reads arrive. And given this time decoupling nature, right, you have this gap in which you can actually do the work after you acknowledge the appends, but before the reads arrive. This is the key idea. So LazyLog makes a very simple yet powerful change to the conventional shared log interface. So in LazyLog, when you append a record, it does not eagerly bind it to the log slot, but rather what it gives you is that It makes the record immediately durable, so it's three-way replicated on multiple disks, fsync's called, whatever. And it gives you a guarantee that the records will eventually be bound to their linearizable positions, right? And LazyLog continues to do the work in the background, but it enforces this ordering before you can expose the log to the external world, right, via reads. So this preserves the abstraction of a conventional shared log, where you have like an ordered sequence of records. It's just the way it performs the ordering at a different point. So conceptually, the way you can think about LazyLog, it is actually behaving like a quantum system, right? So in a quantum system, you have like particles which are in a state of superimposition unless you make a direct observation, right? Once you make the observation, the system collapses and gets to a definite state, right? This is exactly how LazyLog works, right? So when you ingest data into the system, it is durable, but the records are in this fuzzy state, right? Once you observe the log via a read, it collapses, and then it gives you the definite ordering. So you might think this is like a very weird idea, right? Why is this even practical? Well, it turns out to be very practical, right? So here is an example where this is directly useful for an application. So there are many databases which use this pattern called decoupled readers and writers, where the writers are just pumping data into the updates into the log, and the readers, they're reading the content, and then they're building database state out of it, right? So now, the writers in these systems typically do not need to know where their data is appended into the log, right? Only the readers need to see the data records in the linearizable order, right? And furthermore, the readers are typically lagging behind the writers in these systems. You might think this is like probably like one application that you just found by luck, right? But this is not the case. This is actually a conscious decision that many applications take, and they design their systems this way. In fact, this is actually called a very popular paradigm called CQRS, which stands for Command Query Responsibility Segregation. And this software pattern is very popular because it offers you many benefits. There are three key benefits to doing this, right? So first, you can independently, if you split the readers and writers, you can independently scale them, right? This is more similar to how you separate compute and storage. And it kind of avoids the fate sharing between readers and writers, right? If the readers fail, the writers can still operate. And it minimizes the performance interference between these two sets of tasks. So in fact, we conducted an application study, looked at open source applications which are built on top of Kafka. And we found that many of these applications, right, and implementations of these applications actually satisfy these properties. They decouple readers and writers. The readers lag behind the writers in many cases. For example, take the log aggregation one, the last but one example here. So in log aggregation, the use case is you pump in a whole lot of data into the log, but you analyze it much later, right? Which means that the readers are kind of decoupled in time from the writers. And all of these other applications also have the same property. So all of these applications can also benefit from the low latency ingestion, right, that LazyLog provides. So LazyLog changes the interface, right? So here's the new interface. Somebody can tell what has changed now?
Position.
Yeah, it's just a Boolean. So we don't return the index. So this is the only one change that we make to the interface, right? This small interface change actually opens up a very big performance optimization, right? And some people might be worried that, oh, this interface doesn't affect applications. The good thing is many applications actually don't use this returned integer anyway, right? We looked at many application code, the code of many applications, and then we found out nobody's actually using this index anyway. So not exposing this index upon append enables LazyLog to do this work in a more lazy manner. So I want to diverge a little bit and talk about a more general concept right here. So the concept of like interfaces not exposing state to optimize performance is actually a more general idea, right? And LazyLog is an instance of this general idea. So how many of you have heard of this term called Nilext interfaces? I think very few. You're on, oh, maybe, yeah. Okay, I'm actually surprised 3 people know it. Okay, so something new to learn today. So we wrote a paper in 2021 which introduces this idea called Nilext interfaces. So let's take a look at what I mean by Nilext. So we all know what idempotent interfaces are. Dominic talked about this in his talk. The idea is very simple. So you have a system state, you apply an input, the system state changes, but if you reapply the same input, there is no side effect. You can keep doing this multiple times, the system stays in the same state. There are commutative interfaces. In commutative interface, you have two operations, A and B. You can apply them in order A and B, or B and then A. It doesn't matter, they produce the same final state because these operations commute, so this operation, this interface is a commutative interface. Nilext is a sort of like an equivalent property, right? Nilext stands for two terms, nil and externality, which just means that zero externality. The idea is that, let's say you have a system which has a piece of state within it. You allow an update to happen on the system, which actually changes the state, internal state of the system, but the system does not expose this state to the external world by returning the current value or the error to the external world. But rather, it can just say that, I'm done with this operation, right? That's the only contract, right? So if your operation does this, then that is an Nilext interface, right? Now, you might think that this also is kind of like a weird idea, but it turns out like Nilext interfaces are kind of prevalent, right? If you take a look at databases like RocksDB or any other database that is actually built on log-structured merge trees, all of them are Nilext interfaces, including read, modify, write updates, right? Which is the merge operation in RocksDB. And all of these operations are Nilext. So what LazyLog is actually saying is that we should make the append interface of the shared log to be Nilext. That's the prescription that LazyLog is making. So let's talk a little bit about the LazyLog performance property. So appends are always going to be fast because we're not doing the ordering in the critical path. But what about reads? Well, we can say we can be very lazy about when we do the ordering, but this is problematic because you have to do the work while you're serving the read, which increases the read latency. So this is what LazyLog actually does, right? So it keeps doing the ordering work in the background, but it enforces it, if needed, upon a read, right? So naturally, if you take a look at a system that implements the LazyLog interface, it has these two distinct portions. The purple one, which is durable, and it is ordered. And then there is the green one, which is just durable, but it is not ordered yet, right? So the system is constantly moving data from the green portion to the purple portion, where it is constantly ordering, determining the order, and moving the window, right? So the appends happen in this green portion. They are always fast because there is no coordination. But the reads can take two different paths. So if you read an index for which the ordering is resolved, then the read is a fast read, right? You don't have any extra work to do. You just serve it. But if the read comes to a slot for which you have not determined the order, then it takes a slow path, right? You have to do the ordering now, and then you can serve the read. But for many applications, as I mentioned, there is this time decoupling that is naturally inbuilt into these applications, which means that the reads are most commonly going to be fast. But you might ask, there could be some applications which are not having this property. So what happens in that case? So even for those kinds of applications, which is kind of the worst case behavior for LazyLog, it is not worse than a eager ordering shared log. The reason is that in that kind of applications, LazyLog just simply shifts the cost. Instead of doing the work on a write, it does the work on a read. But in most applications, as I mentioned, there is time decoupling, which means that we get the performance benefit. So that is the LazyLog idea and the abstraction, right? Now, I'm going to talk about like the design, the system design, which implements this abstraction. So we built two implementations of this abstraction. It's called Erwin and Erwin-BlackBox. Both these implementations actually give you total ordering across shards, and they give you that in like one round trip time, right? You just need to take one round trip through the network, and you get linearizable ordering. And both of these implementations actually give you about like 1 million operations per second, appends per second in our test bed. But there is no reason for us to suspect why this wouldn't perform on other test beds. The reason we built these two versions is that Erwin actually can work with big payloads, right? You can write like a large message, and you can still get the same throughput. But the black box version actually cannot give you sustained very high throughput for large payloads, but it can do so for small records, which is actually a very popular workload for applications like WhatsApp. But the practical advantage of black box version is that you can take today's Kafka shards without any change, not a single line of code change. You can string them together, and then you can get total order across all of these different Kafka shards with low latency, and there is no total ordering in the original Kafka implementation, right? And it doesn't have to be Kafka, it can be anything, right? So let's take a look at how Erwin works, right? So this part of the talk is going to be a little more technical, so bear with me. So like many shared log implementations, you have the shards down here, right? And then you have the sequencing layer, which is essentially a small Paxos cluster, right? And then you have the clients. So to begin with, the clients actually start writing the data to the shard. Now, there is a problem already here. The problem is that these shards are essentially running a protocol like primary backup or Raft or Paxos or something like that for fault tolerance. Now, if you just treat these shards as black boxes and submit requests to them, then they're going to do some internal coordination, which kind of thwarts your high-level goal of achieving one round-trip appends. So what we do is we break this black box nature of these shards. Instead, we kind of write to the replicas directly from the client, right? So there is no coordination. You just simply directly write a given particular record to all the shard replicas. But there is a very obvious problem here that there is not only cross-shard ordering, even within a single shard, the replicas don't agree the order of the messages, right? On the first shard, you can see that the messages are reordered across replicas. So how do you deal with this problem? So LazyLog, what it does is it splits the data into two pieces, the actual payload and a piece of metadata that identifies the payload, right? And it writes this payload into the sequencing layer, sorry, the metadata into the sequencing layer. Now, the sequencing layer actually tells you what is the order in which you should order these data records. Like, for example, it says that A actually precedes X. The other way is wrong, right? So basically, you can use this information saying that the first slot is A, second slot is X, the third slot is Z, and so on. You can take this information, and then you can pass it to the shards. And then the shards now know that, OK, this is how I should arrange my local log, right? So there is a problem here, though. The sequencing layer, I talked as if it's a single mission, right? That is not the truth. It's a Paxos cluster. So how do you actually write to this Paxos cluster, the metadata, right? The problem is that if you submit this metadata request as Paxos request to this cluster, then there is going to be internal coordination within that Paxos cluster, which again kind of goes against our one round trip goal, right? So what we want to do is we do something like coordination-free sequencing within the Paxos cluster. What this essentially means is we directly write the metadata also in parallel to all the sequencing replicas. And of course, we have just shifted the problem somewhere else now, because although the append's complete in one round trip now, the metadata messages can arrive at different orders. So how do you determine the order, right? Now, Erwin, what it actually does is it does not try to prevent this from happening. It allows this reordering to happen. But in the background, it can establish the correct linearizable order, right? I'll show you how. So here is the secret sauce for doing the correct lazy sequencing, right? So the intuition is that if append B follows append A in real time, which is B starts after append A completes, then all logs will naturally capture that dependency, right? This is like, let's see this with an example. So let's say there are 4 records, and records A and X are kind of concurrent, right? And after that concurrent pair is finished, there is another concurrent pair, which is Z and Y, right? And this ordering is naturally captured in all the logs, naturally. This is because once you finish, that is when you start the next command. That is the definition of happens after, right? So this is naturally captured in the metadata replicas. So to determine to break the ties, like because we have like different ordering across the metadata replicas, we just choose one person as the leader, right? And we take that person as the leader. And all of these orderings are correct, by the way, right? All of them respect the real-time linearizability requirement. It's just that it's convenient to just choose one node, right? We just choose that node and then say that that is the order. So we send this order to the shards, right? Now, the key technical problem here is that once you have sent this order to the shards, it's possible that this current leader could fail, right? And you must be careful that you have to preserve this order, because once you have given this order, it is possible that you have served reads based off of this order, so you cannot go back and change your mind, right? So you must preserve this exposed order even if the current leader fails. And here is the key kind of like a, if you like proofs, here is the invariant which actually holds the protocol together, right? We call it the stable global position invariant, which essentially means that for records which are before the stable GP are the ones that are stable in the system, which means that their order is guaranteed not to change even in the face of leader failures. And it is guaranteed that this order will remain unchanged regardless of future leader failures. And the shards are supposed to serve reads only up to the stable GP. So when can you advance the stable GP is the question now, right? So the stable GP can be advanced only after the leader has disseminated this ordering information to the shards and the entries, the corresponding metadata entries in the sequencing layer have been garbage collected. So once you have advanced the stable GP, the system gives you the guarantee that anything before the stable GP is all stable. So you can expose all sorts of order before that point. But anything after the stable GP is kind of unconfirmed. You cannot expose that order. And that is the safety, kind of like the invariant in the system. So there is like several other failures that I have not talked about that the system actually handles. For example, when you're setting the metadata and the data, like there is no guarantee that both of them will reach the servers, right? Like you could write the metadata but then fail before writing the data, or the other way around, and there are several other cases, right? So Erwin actually has mechanisms to deal with all of these cases. So the Erwin implementation that I showed you actually intrusively modifies how the shards internally work, right? So one question that we thought about was, how do we actually make the solution more practical? Can we support the same idea by not modifying the shard data, right? Can we take Kafka shards and actually establish global total order with low latency? And surprisingly, you can do that, right? And in fact, you can actually take anything like Kafka or RedPanda or your favorite Raft implementation or anything that you like that gives you total order within that shard, and it gives you durability within that shard. If you have such an implementation, then you can string together many such implementations and obtain a total order across them with low latency, right? So the way this works is, so in Erwin, the clients actually wrote the data to the shards, right? If you do that, the problem is that then you have like coordination within this, the shards. So let's say if you're running Kafka here, you write a piece of data into a Kafka shard, then Kafka is going to run its own internal coordination algorithm to order the records, right? So that will actually avoid your, or prevent you from achieving low latency. So instead, the idea is very simple. Actually, instead of sequencing just the metadata, just sequence the data, right? Through the sequencing layer. So then you can lazily sequence the data itself in the background, right? So, and this is the reason why I was telling this solution does not scale for bigger payloads, because the data itself is passing through the sequencing layer, right? So that the NIC of the sequencing layer actually becomes a bottleneck, right? So there is a limit on how many messages you can process per second. But we have seen that if your payloads are very small, right, as big as your metadata records, then you can still achieve 1 million appends per second, which is actually surprisingly common in many workloads. So, as Hans mentioned yesterday, I cannot finish a talk without performance benchmarks, so I'll show some numbers now, right? So we did all of this work. Like, so what is the latency benefit of Erwin or lazy ordering in general, right? So here is a workload. We append 4 KB records into the system. We run 5 shards. You can arbitrarily choose any number of shards, and then each shard has 5 replicas within it, 3 replicas within it. And here is the data, right? So I wanted to pay attention to the y-axis. It's like microseconds, tens of microseconds, right? And Corfu is about like 60 microseconds. We gave all the implementation benefits for Corfu in that we use a kernel bypass, we use RDMA, and all sorts of implementation gimmicks to make Corfu faster, right? This is our baseline. And Erwin, even after giving all of these good implementation tricks for Corfu, we reduced the append latency by 3.6x, and we also reduced the P99. And I have not even shown Kafka because it is impossible to show here. It's like 100x faster, right? And we provide total order. And how do reads perform in LazyLog? So we perform a workload where we append data and then read it back, right? And there are two configurations, right? As a researcher, it's a very bad practice to just show the good cases for you. Also need to show what is the downside of your system, right? So this graph shows that. So in the top graph, we are reading, mimicking real applications where there is a lag between the readers and the writers. And in the bottom graph, we're just like not doing that. We are just forcing the system to behave in a bad way, right? So for many applications where the behavior is very similar to the top graph, you can see that compared to Corfu's implementation, LazyLog reduces append latency, but it also has the same read latency, right? It doesn't optimize the read latency, and it does not make it bad. That's great, right? So it's a total win. But in the worst case, right, when there is no lag, which is not common for applications, but anyway, you can see the behavior here that we reduce the append latencies, but because there is no delay and you're very eagerly reading it back, you just shifted the cost, right? And that is why you see that the read latency of LazyLog is worse than Corfu. But like the total time to append and read is essentially the same. The summation of these two things are the same. And we also built a bunch of applications on top of LazyLog's interface, right? A key value store, an audit log, a journal for stream processing, and so on. I'm just showing the results for a key value store implementation here. This key value store, similar to the database, it has a decoupled reader and writer arrangement, and the appends actually log. On a put, you just append the entry into the log, and for serving the read, you consume the log, build state, and then serve reads out of it, right? And as you can see, for write-heavy workloads, Erwin actually reduces the latencies quite significantly compared to Corfu. For read-heavy workloads, it's still a little bit better, but like we don't optimize the reads in any way, so it's fine. So to summarize this part of the talk, so what I showed you is that eager ordering shared logs incur high latencies, and eager ordering is actually not needed for many applications. And readers are time decoupled from writers in all of these applications. And if you're clever about how you do the ordering, then you can actually achieve low latency ordering or low latency appends, and which is what LazyLog does, and it's a new shared log abstraction. And we can do this for real applications, not only achieve like low latency appends, but also have little overhead on reads. And the software LazyLog's implementation is publicly available on GitHub. I welcome you to use that. And I want to finish with one limitation of LazyLog, right? The limitation of LazyLog is that it does not reduce end-to-end latency. It reduces ingestion latencies. End-to-end latency means that what is the time between when you ingest the data into the system and when the downstream tasks can derive insights from the data, right? This is very critical for applications like high-frequency trading, where you're looking at stock ticker prices and placing orders, or real-time analytics and real-time search, where the metric that matters is how quickly can new search results show the newly ingested data, right? And LazyLog does not actually help with these applications. And we have a newer paper that is going to appear soon in this year's OSDI. It's called SpecLog, which actually reduces this metric of latency. And the key idea in SpecLog is to speculate the order of records and start the downstream computation based on the speculated order, right? And if the speculation is correct, then you have basically overlapped the computation on the ordering coordination required within the shared log, which is a win in terms of end-to-end latency. And to ensure that the speculations are highly succeed with high probability, we have a new ordering mechanism. Because of time constraints, I'm not going to talk about this, right? And we have shown that this reduces this critical time to insight latency in many applications like high-frequency trading and real-time search and so on. So I want to end the talk with a couple of remarks. Logs have been around for many decades, right? And even then, new environments and new ways of applications on how they use the log, that gives you a new opportunity to design better log abstractions, right? And by paying careful attention to how the applications consume these very fundamental abstractions, you can come up with new ideas to fundamentally change how these abstractions work in the modern application scenario, right? So I'll finish this talk here. And we're, of course, open for industry collaborations. We're always looking for practical problems to work on. So if you're interested, just contact me. And here is some links to the group website. Thank you.
Thank you.